do part 2 on Monday. So 12.5, we're going to talk about arc length, and curvature. All right, so we've been relating several things that we've talked about with vector valued functions back to what we talked about with parametric equations. And we said before for parametric equations that the arc length, if we have x for our parametric equations, x equals some function of t and y equals some function of t. These are our parametric equations. On some interval, that our arc length s equals the integral from a to b over whatever interval we're looking at, the square root of x prime squared plus y prime squared. dt. Now if we worked with this with our arc length integral with parametric equations, if we let our functions, if we want our curve to be represented by a vector valued function, so r of t is a vector valued function, is x of ti, like we've been doing, x of ti plus y of t j plus z of tk. We can use the same kind of arguments to define our arc length using vector valued functions. So I'm just going to write if r of t equals this vector valued function, then s, our arc length, is just our integral over our interval from a to b, t equals a to t equals b, of the squares of each of our components. So it's going to, or the derivatives of each of our components. X prime squared plus y prime squared plus z prime squared. And I'm just dropping the function notation, but we're understanding that these are all functions. So this is our arc length in using vector value functions. This quantity, square root of x prime squared plus y prime squared plus z prime squared, what is another way that we can represent this? What is the square root of x prime squared plus y prime squared plus z prime squared? The magnitude of r prime. Very nice. So the r prime magnitude equals this big square root. X prime squared plus y prime squared plus z prime squared. So we can write our, clean that up a little bit. So we can write our arc length for a vector valued function s equals the integral from a to b of the magnitude of r prime dt. And our limits, our conditions, is that our curve is smooth on a to b. So we don't want any sharp points or anything like that. So our curve is smooth on our interval. So let's remember this integral, because it's going to come up here in just a minute. This expression for our arc length. We're going to be using this in just a minute. So this gives us a way to calculate arc length with vector value functions. Now, do you guys remember what usually happens when we're when we're trying to calculate arc length. The integrals are very messy, usually, because you have these squares and this radical. So the integrals, usually you have to have a nice function to calculate an arc length easily. Let's just look at a quick example of an arc length calculation. So we have r of t equals t I plus t squared k. And we want the arc length from 0 to 4. First of all, what is this curve going to look like? If we sketch this in the xz plane, what would this curve be? What is it? Someone said it? A parabola. This is part of a parabola. From 0 to 4, it's just going to look like this. In the xz plane, we have z equals x squared. So we want the arc length. We want the length of this curve from x equals 0 to x equals 4 here. So our arc length, is going to be the integral from 0 to 4 of the magnitude of r prime. So we're going to get the square root of 1 squared plus 2t squared dt. So I get the integral, I'm just going to simplify that, 1 plus 4t squared dt. So, question? This one might be in the back of the book, in your table. If it's not, how are we going to approach evaluating this integral? Trig substitution. This is a trig substitution. So it's a nice trig substitution integral, but it actually turns out to be, there's part of it that's a little tricky. If we do our trig sub, I'll sketch out. I'm not going to go through the entire integration, but I'll write the substitution. This is square root of 1 plus 4t squared on this side, and I'm going to do 1 on this side and 2t on that side. So we get from this the square root of 1 plus 4t squared equals secant theta. And our dt from our triangle t equals tangent theta over 2. So dt comes out to be 1/2 secant squared theta d theta. So we end up with the integral, if we're looking at just the indefinite integral, I'm not going to put my limits in. So we end up with the integral of 1/2 secant cubed theta d theta. So this one is a tricky one to evaluate. Anybody have an idea of how we evaluate this one? We have to do integration by parts. So we do a trig sub, and now we have to do an integration by parts. When we do the integration by parts, we end up with one of our integrals being the integral of secant theta, which is another tricky integral to evaluate. So we end up with kind of 3 nested levels of tricky intervals here. I'm not going to go through. What's that? So if you do integration by parts, I'm just going to write over here u equals secant theta and du equals secant squared theta. dv, sorry. That would be your integration by parts, and you end up with, as if you go through it, you end up with 2 the integral of secant cubed theta equals secant theta tangent theta plus the integral of secant theta. And this one is a tricky one to evaluate also. So I'll go that far, and if you want to do it, you can go from there. So this gets you started. But finally, this is a good one to know how to do. It's a nice trick that you do to get this integral, and it's one of those that comes up fairly regularly. This one is definitely one that's in the back of your book. So finally, our integral, we end up with the integral from 0 to 4 of the square root of 1 plus 4t squared dt equals 1/4 2t times the square root of 1 plus 4t squared plus 1/4 natural log of the absolute value of square root of 1 plus 4t squared plus 2t evaluated on 0 to 4. And if you plug this in, evaluate this, you get finally that the arc length is approximately 16.82 units. So just like we expected, calculating the arc length of even a simple curve can get complicated very quickly. Now our main purpose here with this lesson is not necessarily to look at arc length. We need to be able to calculate arc length, but we're going to look at curvature. Is everybody good with what we have here so far? So we're going to talk about curvature. We're going to develop this idea of curvature. We want to quantify the curvature of a curve. Now let's start our analysis by looking at a curve. Here's my curve. And I have a point here at t equals a, and another point here at t equals b. And my arc length goes from there to there. Now if we start here at time equals a and we go to time equals b, if we consider the arc length, we're thinking of the arc length as a function, and I'm going to make this a three-dimensional coordinate system. If we consider the arc length a function of t, so for any particular time, as we're traveling along this curve, the arc length is going to vary as a function of time. Is everybody with me there? Can we all agree that for any particular time, the arc length at that particular time is going to uniquely define a point on my curve? If I consider the arc length as a function of time, and I plug in a t into that function, that function is going to give me a point on the curve. If I start at t equals a and say t equals 3, and I'm here, and we know the arc length for t equals 3, that's going to define a point on the curve. So we're considering arc length as a function of time. So we're parameterizing the curve with respect to arc length. So we're going to say that s of t, or arc length, as a function of time, and we just defined arc length for a vector valued function, is the integral from a to b of r prime of the magnitude of r prime of u du. And u is just a dummy variable for the integral. So the arc length is just this integral. So at any point on my curve, the arc length is going to be given by this integral. So this is how we would find my point on the curve, because we can find the arc length. So we call s of t equals the integral from a to b of the magnitude of r prime, and I'm just going to write all of our different formulas. That equals the integral from a to b of the square root of x prime squared plus y prime squared plus z prime squared. And we're saying this is a function of our dummy variable also. This is the arc length function. And this arc length function is going to play an important part in what we do for a good part of the semester. And we call S is the arc length parameter. So this gives us a way of parameterizing our curve with respect to the arc length. And each value of the arc length is going to give us a unique point on our curve. Now let's think back to, now I said we needed to remember this function. So if s of t equals the integral of r prime of u du, the fundamental theorem of calculus tells us that ds dt, I'm going to take the derivative of my arc length function, that ds dt equals the magnitude of r prime of t. So can someone interpret this for me? Right. The arc length. So if you take the derivative of the arc length with respect to time, you get the, what is the magnitude of r prime? How did we interpret that in terms of speed? The derivative of the arc length with respect to time gives us the speed of the particle traveling along that curve. So this is the speed, if we're thinking about this as motion in space. So the derivative of arc length with respect to time is the speed of the moving point. So this is another way of looking at the speed. The speed is the rate of change of the arc length with respect to time. That tells us how fast we're moving along that curve. And we're going to use the arc length parameter to define the curvature of our curve. The arc length parameter is going to tell us something about the curvature. So let's move on to our curvature. So we talked about our arc length parameter, parameterizing our curve in terms of the arc length to define a point on the curve. We're going to use that idea to help us define curvature. So let's look at a couple of curves. Here's one, and we're going from A to B. And here's another one, and we're going from A to B. And so just thinking intuitively, which one has greater curvature? The one on the right, so I'll call this 1 and 2. So this one has greater curvature. We want to be able to quantify the curvature. We want to get some kind of information about the curvature. Anybody have an idea of what is the curvature? What is it related to? So Danny said acceleration. And thinking geometrically, if something's more curved, when we think of a curve, if we have a circle, see if I can. If we have a circle. There's one circle. I'll do it this way. There's one sort of circle, and there's another circle. Which of these circles has greater curvature? The one on the right. So what is different about this circle than this circle, geometrically speaking? It's smaller. What specifically is smaller? The radius. The radius is smaller. So curvature has something to do with the radius of the curve. So we're going to talk about the radius. It has something to do with the radius. Now, because we want to quantify curvature, we want to talk about what's changing here. Does anybody have an idea about how we can talk about something changing with these curves in terms of what we've been talking about in the last few days? Let me draw another couple of curves. Okay, Scott said something that makes sense to me. Let me draw a couple of things in here, and so I've drawn in some tangent vectors. And I'm going to draw in one more on this one. So here are some tangent vectors. And let's say this is point A and this is point B. And I'm going to say that the arc length between A and B on both curves is the same. What's changing here? The tangent vector, the direction of the tangent vector. So the arc length, or the curvature, we could say the curvature has something to do with how the unit tangent vector is changing as we travel along the curve. So when the curvature is higher, is the tangential vector changing more or less rapidly? More rapidly. The unit tangent vector is changing more rapidly when we have a higher curvature. So motivated by that, motivated by our little discussion, we're going to define our curvature. And I had a professor in college that said, when you make it your definition, they can't touch you. Meaning, it makes mathematical sense, so we're making this our definition. It's not, we've developed an argument, so now we're going to define curvature in this particular way. Doesn't necessarily mean it's right or wrong. We've chosen that definition, and we're going to follow that definition from here on out. So we're going to define the curvature. And we call curvature K as the rate of change magnitude of the rate of change of the unit tangent vector with respect to the arc length. So as we're moving on this curve from A to B, the tangent vector, the derivative of the unit tangent vector with respect to the arc length is, the magnitude of that is smaller than the rate of change of the unit tangent vector with respect to arc length when we have a higher curvature. So this is going to give us, this definition is going to give us a lower curvature here and a higher curvature here. And we call this the magnitude of T prime with respect to S. And this is for a smooth curve given by some function. We're parameterizing our curve by the arc length. And our radius of curvature. We talked here about the radius. So when the curvature is smaller, the radius is larger or smaller. When the curvature is less, is the radius bigger or smaller? Bigger. And when the radius is large, when the curvature is large, the radius is small. So the curvature and the radius are inversely related. So we're going to define our radius of curvature is 1 over k. So these are our two quantities that we've come up with related to curvature. So this gives us a way to measure curvature, to calculate curvature. Anybody see a problem here, though? What did Emily, when you worked on the homework from last night, calculating t and n and a sub t and a sub n? Lots of algebra, and we're parameterizing. This is t with respect to the arc length. So we're parameterizing our curve with respect to arc length, and we're taking the derivative. And think back to how we defined our arc length, that integral with the radicals and the squares. And when we calculated our arc length, how complicated that can be. So we want an easier way to quantify our curvature. So we're going to figure out how to get back to our original parameter. But it's important to remember that curvature is defined as the rate of change of the unit tangent vector with respect to arc length. So that's what parameterizing with respect to arc length gives us. The radius of curvature is 1 over the curvature. All right, so we want to go back to our original parameter. So I'm going to switch pages here. So we want to represent our curvature in terms of the original parameter. It's not too difficult, and luckily it's kind of nice. So we have that k is the TDS, the magnitude of this, and we're going to use the chain rule. We're going to use the chain rule and say that equals. Oops, and I forgot my vector here. There we go. The TDS. I'm sorry, dt times the TDS. This is our arc length. Yeah, that's our arc length. Small s. Usually we use capital S for surface area. So the arc length is our small s. And I'm going to rewrite this as dt divided by ds dt which is dt dt. How can I rewrite this? T prime. And ds dt, s prime, which is what is it, Caitlin?
R prime.
R prime, yes. ds dt is r prime. So our curvature is t prime, the magnitude of t prime, with respect to t, over the magnitude of r prime with respect to t.
You have to separate out the magnitude?
No, you can do one big magnitude. Now t prime can be a little tricky to calculate, and we went through some derivations yesterday to find our normal component of acceleration. So yesterday we found that we're going to simplify this even a little more. Yesterday we said that a sub n, and I mentioned that the curvature had to do with our normal component of acceleration. A sub n equals the magnitude of the velocity times the magnitude of t prime. And we said that was v cross a magnitude over v magnitude. So this is one of the formulas we came up with yesterday. So this tells us that t prime, the magnitude of t prime, equals v magnitude of v cross a over the magnitude of v squared. And I can rewrite this if I just want to write it in terms of my original vector valued function. So finally k equals r prime cross r double prime, magnitude of that, divided by r prime cubed. So this is t prime, and we're dividing that by r prime, which is just v. So my curvature is r prime cross r double prime, the magnitude of that, divided by the magnitude of r prime cubed. This formula is usually going to be the easiest to compute with to find your curvature. And this is for a vector valued function defined in space. All right, let's look at a quick example of calculating curvature. And then we'll talk about a shortcut. If we have time, we'll talk about a shortcut in rectangular coordinates. So we have r of t is 2t squared plus tj plus 1/2 t squared k. Yeah, I forgot my I hat. Thank you. So here's my r of t, and we want to find k. So r prime, what is r prime here? For t I plus j plus tk. R double prime for I plus k. The magnitude of r prime. Square root of 16t squared plus 1 plus t squared. So I get square root of 17t squared plus 1. And the magnitude of r prime cubed is 17t squared plus 1 to the 3/2. And r prime cross r double prime. I'm not going to go through the cross product, but we end up with I minus 4k. And the magnitude is square root of 17. So k, finally, our curvature is a square root of 17 over let's see, did I do that upside down? Yes. No, that's right. I'm sorry. I was thinking of the radius. Square root of 17 divided by right, 17 t squared plus 1 to the 3/2. There we go. So there's our curvature. So at any time t, we can find our curvature, and we can also find our radius of curvature. All right, we'll talk about our shortcut for a curve in the plane on Monday for finding curvature, and we're going to talk a little bit more about curvature on Monday as well. But we came up with a way of defining curvature, way of quantifying curvature, and talked about its relationship to the arc length and to the normal component of acceleration. So we have a lot of, if we have a large normal component of acceleration, we're going to have a larger curvature on our curve. Questions? All right, let me give you your homework. There you go.